Good afternoon, everyone. My name is Franca Tamaris. I'm the Events Coordinator for the Melbourne Energy Institute. Welcome to our seminar today on liquefied natural gas and export. Before we begin, I'd like to acknowledge that today we are gathered on the lands of the Wurundjeri, Woiwurrung and Boonwurrung people who have been custodians of this land for thousands of years, and we acknowledge and pay our respects to their elders, past and present. Thank you all for joining us today for the third seminar of the MEI Seminar this year, focusing on gas. We have some interesting seminars scheduled for the year. Some instructions for our online audience. If you have any questions, please enter them into the Q&A box as the chat function is disabled. We will have time for Q&A for both the online and audience in the room at the end of the session, and we'll endeavour to get through as many of the questions as we can. Now, to introduce our speaker today is Carolyn, LNG advisor at Shell Australia. Carolyn is a chemical engineer with 25 years of energy industry experience in the gas and LNG sector, beginning her career in Perth, WA. After joining Shell in 2007 in The Hague, the Netherlands, and starting as an LNG and gas technology design engineer, she worked variously in research and development and technical support for Shell-operated and non-operated ventures. Carolyn then moved into LNG operations and asset management, spending 7 years on Sakhalin Island in Russia, where Shell operated a two-train LNG facility, and then 3 years at the Shell GQC LNG facility in Curtis Island, Gladstone, Queensland, upon returning to Australia. Carolyn is now based in Brisbane and continues to be an advocate for how LNG has delivered valuable energy and improved the quality of life for many in the world. Moderating today's seminar is Professor Catherine Mumford, Head of Department of Chemical Engineering here at the University. Thanks for joining us, and now over to you, Carolyn.
Thank you so much, Franca. I'm just peering over the lectern here. So hi, everyone, for coming. Thank you for coming in, and to those people online. So as Franca has introduced, I have been working in the energy industry for almost 25 years now, and directly in LNG for 18. So I'm very passionate about LNG. I consider LNG to be my baby, particularly from the technical perspective. This is the second opportunity I've had to speak to you about LNG. There's been some updates since 2022 when I was last here, particularly in the decarbonisation of the supply chain space, and I'm looking forward to sharing that with you. So I'd like to start by setting the context of why we're here today, talking about energy in general, and liquefied natural gas specifically. The world today is very dynamic and fast changing, and for all of us, energy is a very defining feature. So our lives and our livelihoods, our communities and economies depend on a convenient, reliable and affordable energy source to thrive. The population of the globe is growing and demand for energy will continue to grow, but meanwhile, we also do need to address major stresses on the environment, and in particular climate change. That has been something that has never been more apparent and more important to us. So I'll move on to my presentation. The presentation is basically 4 areas. Firstly, some fundamentals about LNG, a bit of history about it, some considerations of the aspects that drive the so-called value chain, and then the place LNG has in the global energy mix and demand, and finally where the LNG supply chain space is with regards to our decarbonisation journey. So firstly, this may be something that many of you are already aware of, but I'll go quickly through it again anyway. What is natural gas? Basically, it's a generic term that refers to a mixture of light hydrocarbon components. It's generally mostly methane, anywhere up to 98%, with a few heavier components such as ethane, propane, and butane. So the actual composition of any natural gas depends on the reservoir which it's been extracted from, and also the market that it is going to be consumed in. So the chart in the top right shows a number of different sources of LNG, their Wabi index, and the fields and the regions where they are produced and used. The natural gas heating value and composition can actually be tweaked while we're producing it, and also at delivery to allow entry to different markets. The cost of natural gas is based on its energy value, and by that I mean it's bought and sold at a cost which is basically per million BTU or terajoules. This is a little bit different to oil, which is cost per volume or per barrel within a density range. So when you cool down natural gas to minus 162 degrees, it turns to a liquid, and that makes it much more safer and efficient and convenient to transport on a high volume basis. Its volume basically has reduced to 1/600th, so it's easy to ship to locations of the world where it's used. So one quite rapid evolution that's happened since I last spoke with you on natural gas is its origin. So up until recently, we'd always considered natural gas to be exclusively a fossil fuel, basically created by the decay of plants and animals, organic matter, buried under layers of rock. Geological time creates pressure and temperature, and then it generates traditional hydrocarbons, so like the oil and the gas. But as we look now to low carbon forms of natural gas, there are newer and more nascent forms of gas. Those aren't created over millennia, but they're actually chemically formed, such as synthetic natural gas and biogas, both of which can be liquefied and transported, and I'll be talking about those later in the session. So moving on to the why of LNG. Well, as I said before, turning natural gas into LNG allows the effective distribution of energy to the end users. So economies and industries, homes, gas fields, the sources of gas tend to be in fairly distant and quite inconvenient locations. So a lot offshore, deep water, making it hard to access. By producing and liquefying natural gas, it enables the international trade of energy, provides energy and energy security for countries which do not have their own natural resources, and it therefore allows flexibility and reliability for where gas is sourced and where it's used. In the past, pipelines were a common method of delivering gas to users. The technology of a pipeline is quite simple. We're all familiar with it and works very well, but at longer distances, they do start to become very economic. You need a lot of compression station, a lot of power. It's also not very flexible to change capacity. And a recent example of how a pipeline can be quite limiting is the Russian pipeline gas, which used to be a major supply of energy to Europe. Since the situation in Ukraine, much of that method of supply has actually been cut off by sanctions, and so the import of LNG via the sea has filled part of that energy gap. The environmental impact of LNG as a baseload fuel supply to power plants is much lower than coal. Natural gas produces about 50% less greenhouse gas emissions and significantly improves the air quality. So fuel gas-fired power stations don't produce the same significant particulates and SOx components that coal-fired power does, which results in higher air quality, less respiratory health impacts, and the smog that is very visible in coal-fired areas. And then finally, so as the world moves towards low carbon and renewable energy sources like wind, solar, and hydro, natural gas still there provides balance and resilience by being available when the renewables are not available. So when the wind's not blowing, the sun is not shining, power demand can still be satisfied by natural gas, and the resilience of our networks can be strengthened. So getting on to how LNG is produced. Well, the fundamentals of making something cold are quite mature. We've all got a version of it in the home. It's our refrigerator. Uses the Joule-Thomson effect to cool a fluid and reject heat to the atmosphere. An LNG facility uses the same thermodynamic basis, but just on a more efficient and a much larger scale. So once you've sourced the gas, you need to clean the gas to remove impurities such as CO2, H2S, nitrogen. Then you need to dry the gas, remove water to avoid those components and water freezing up, blocking up the process, but also to comply with the end user specification. Once you've cooled the gas to liquid, you need to store it, and then, of course, you need to deliver it to the customer. So the whole process is quite energy intensive. you need about 7 to 8% of the fuel to natural gas to be consumed as fuel to produce LNG. There's two main technologies which are common in the baseload LNG production world. So it's the mixed refrigerant process, where you could have a single mixed refrigerant or a dual mixed refrigerant with a propane pre-cool cycle and a main refrigerant cycle. The second type, which is now quite prevalent in the United States, is the cascade process, which uses pure components. So we'll use a propane cycle, an ethylene cycle, and a methane cycle. In terms of the equipment, there's really just a few key pieces of kit that define the success of an LNG plant. You have the major heat exchangers where gas undergoes the cooling, the compressors and the turbine drivers, which circulate the refrigerant, and the storage tanks, which hold the produced LNG. So LNG is actually a relatively modern history. Scientists did first experiment with cooling pure components to liquid from the mid-1800s. So we know the very famous names Faraday, Kelvin, and Joule. It was in 1886 that the first liquefaction of methane was achieved by a Polish chemist, Olszewski. And so that, by definition, was the first production of LNG. So the first purpose-built facility for liquefied natural gas was built in the United States in 1918 with the intent of actually extracting helium for wartime purpose. The first commercial facility for LNG was built in 1941, also in the United States, in Ohio. But unfortunately, that facility suffered what we still consider the worst incident in LNG history in 1944. One of the LNG storage tanks leaked and vaporized. Gas flowed into the neighborhood, ignited, exploded, and leveled part of the city of Cleveland. So after that, it was about 15 years later that LNG was for the first time shipped across the oceans in a 2,000-ton vessel called the Methane Pioneer. So it would have been the first real move of international trade of LNG. These days, the largest modern LNG vessels carry up to 120,000 tons of LNG. The international trade really got going from the 1960s into the 1970s, from Algeria to the UK. And Australia, our own foray into LNG began from the northwest shelf of WA, shipping LNG to Japan from the late 90s. And now the countries in the world producing and trading LNG are Nigeria, Malaysia, Brunei, Oman, Qatar, Russia, the United States, Egypt, Trinidad and Tobago, Peru, Papua New Guinea. So it's quite a big industry. Total LNG trade at the moment is about 407 million tonnes per annum transported across the globe in over 600 purpose-built LNG carriers. The largest importer of LNG in the world is China, not surprisingly. They take about 25% of the global total. Asia is a big market for LNG, so the next highest importer is India at around 7% of the total. And for Australia, it's actually our third largest export commodity by value, 69 billion Australian dollars, and we are the second largest exporting company after the United States. So 3 years ago when I spoke to you, we were the largest, and we've just been pipped just by a little bit. So when we talk about the LNG value chain, really, it's just the phrase that covers the journey of a molecule of methane, which starts from the reservoir through the wellhead, where it comes to the surface. It's then treated, goes into a liquefaction plant, cooled to liquid, then is loaded onto LNG carriers, sailed across the seas to its export destination. The chain continues at the destination. As it's unloaded, it then has to be turned back into natural gas in a process called regasification before it's able to be delivered to end users via the domestic piping network to be burned for energy. Perhaps a key takeaway from this picture is that the infrastructure investment to enable LNG is actually very high. You have your gas exploration and production, you have your liquefaction plants, you've got special storage and jetties, you've got special transport ships, storage and regas facilities at the end user, and really the compatibility, the standardization and integration of this sort of infrastructure globally has been practiced and improved at significant cooperation between the buyer and the seller. So this value chain really has taken decades to perfect. Just a few words on how LNG is commercially traded. So LNG does differ from the traditional oil market, that typically you have a long-term relationship between the buyer and the seller. That's because facilities are very expensive, tens of billions of dollars. They take a long time to develop and build. So generally 4 to 6 years for the development phase, and then another 4 to 6 years for the actual construction. So to support that kind of investment, you need a long-term sales and purchase agreement to be signed between buyer and seller, and they usually cover timeframes of 10 plus years. That gives security of supply to the purchaser, and it gives security of to the supplier to know that someone is going to continue to take their product. Particularly for LNG buyers, for certain countries where their only source of supply is LNG, if you don't get the product, then the lights don't go on. So that's quite a significant dependency that they have. Some LNG buyers take small ownership in ventures just to make sure that they have a seat at the table when these important decisions are being made. So LNG can be delivered commercially in 2 ways. We call it delivery ex-ship or free on board, and that defines where the ownership of the LNG changes hands, and also therefore who is responsible for the shipping. On the shipping side, I'd mentioned there's over 600 of these purpose-built vessels which cross the globe. They can be owned by the buyer or the seller, or they can be chartered. LNG carrier charter rates do fluctuate, but they can be very expensive, anywhere from $50,000 a day to, I've seen $400,000 a day, really depending on the demand. So that cost is factored into the price of the LNG, and the criticality of a very smoothly running shipping operation has a significant financial income. LNG is also more complicated than oil and coal because it's a use it or lose it fuel. By that, I mean LNG will boil off. It boils off at 0.07% per day. So speedy delivery and well-managed storage and usage is very important. During COVID, I think you probably heard stories of crude carriers being purchased at really low prices to be sailed around until the price increased. You can't do that for LNG. When you have your LNG cargo, you need to take it to the point of use fairly quickly. So on pricing of LNG, the primary references are you can have it against the oil price, you can have it against the Henry Hub gas price, or for the Asian market, we use something called the JKM, or the Japan Korea marker. And there's also the legendary spot cargo. So a spot cargo is a cargo that's not really part of the normal contracted quantity. It's often demanded in peak seasons. It can be very lucrative. So if you have a very cold winter in the Northern Hemisphere, then you could be selling a cargo that fetches you 2, 3, 4 or 5 times the price of a normal cargo because of the demand at that time. So as I said, for end users of LNG, you need to turn the liquid back into a gas by vaporization or through a regasification plant. It's the reverse of how you make LNG. You're putting heat back in. It still requires a facility that uses technology, and the most common technology is the open rack vaporizer, which uses seawater, which is very readily available at LNG terminals, as they're generally on the coast in ports and in coastal areas. There are also some LNG terminals which are located inland, and you can use ambient vaporization and heated vaporization. I have a little picture of an FSRU in the middle there. That's a floating storage and regasification unit. So that reflects the fact that it's expensive to build fixed LNG storage. And sometimes what can be done is that there are different solutions. You can use an older LNG carrier to be redeployed as your storage vessel, and a regasification unit on a separate vessel, which allows you to regasify your product with slightly less investment. It gives you a little bit more flexibility. In the last few years, there's been a very fast emerging group of users in shipping and heavy road transport sectors. So LNG generates 25% less emissions than diesel and marine bunker fuel. And so there is actually a changeover driven by both social expectation and a legislative mandate for greenhouse gas emission reduction. Now, given that 90% of the world's physical goods are shipped by sea, this is quite a sizable contribution to reduction of greenhouse gas emissions. So this chart just shows a very clear year-on-year demand for new build vessels with LNG propulsion and the related demand of LNG as a shipping fuel, which with a more than twofold increase between now and in 5 years' time to 2030. And that's kind of a good segue into the next section, which is the future LNG demands of the world. So LNG demand at the moment is around 400 million tonnes per annum, and it's projected to increase to just under 700 million tonnes by 2040. Now, of course, I know forecasting, it's an art. It's informed by global dynamics, and kind of black swan events like pandemics and wars and changes of government can result in very different actuals and estimates. Last few years' demand projections were a little bit higher than this year, so there is some fluctuation. It is slowly coming down, but it is still a significant increase in demand. The top LNG importers of the world, as I mentioned before, Asia, China, Japan, South Korea, India, Taiwan, and very recently Europe. So Spain, France, and the UK have increased their LNG import as a consequence of the Russian gas sanctions. Take a little sip. So what is driving demand? Well, population growth, we've already mentioned that. The current world population of 8 billion, projected to rise to nearly 10 billion by 2050. More people need more energy. Very interestingly, data centers and AI, they are also large consumers of electricity. They're acquiring, cleaning, managing huge amounts of data. And as there's no doubt that AI is going to continue to grow, its energy consumption will also grow. With our move towards net zero, so very energy intensive industries like steel, aluminium, concrete, they need large amounts of energy to run. The shift from coal to gas sees up to 50% reduction in emissions. Similarly, in the power generation sector, the world's largest consumer and producer of electricity is China. And they also are the world's largest consumer of coal for power. So they consume over half of the global demand. By comparison, in Australia, we're only 1.5% of the world's consumption of coal. China expects to hit peak coal in 27-28. It's still building coal-fired power plants, but it is also increasing its gas demand by 6 to 8% year on year. Now, there is a forecast shortfall of LNG supply, which begins to open up in 2034. It's that white triangle in the left-hand chart. This is basically where the confirmed current LNG facilities in construction have come on stream. And it does show that basically we do need more liquefaction capacity going into 2034 to meet future demand. And in terms of that capacity and production, the top producers in the world, I'd mention them, the US, Australia, Qatar, Russia, Malaysia. There is also currently new LNG capacity being built in the US still, Qatar, Nigeria, Abu Dhabi. So yeah, demand and supply are still working their way out. This is a nice infographic of where Australia's current LNG capacity is. Most of the production is in the north of Australia and the west of Australia. All of that gas is actually offshore gas. On the east coast, where we are, we've got 3 LNG facilities on Curtis Island, and all of that gas is actually onshore gas from coal seam methane. So now moving on to some words about decarbonising the LNG supply chain. So since I last spoke in 2022, the efforts in decarbonisation inside the LNG supply chain have become quite clear. There are a few emerging directions, and decarbonisation is driven not only by suppliers but by customers. So 98% of importing LNG buyers actually have a net zero commitment. One effort is to reduce the carbon intensity of the existing LNG production process and infrastructure. As I'd mentioned before, making LNG is actually very intensive. You need to spend about 7 to 8% of the gas for fuel, for compression power, generally in gas-fired turbines, and also to supply energy for other parts of the plant and process. So electrification of LNG facilities using renewable energy will reduce the emissions otherwise generated by fuel gas. There are some existing LNG facilities that are looking at options to convert their existing gas turbines to electric motors, and there are other facilities in construction right now which are all electric drive by design. Another way of reducing emissions from gas firing turbines is by utilising different fuels. So adding hydrogen to gas and using that in turbines reduces carbon emissions. That's quite a fascinating topic because it has to be enabled by the supply of hydrogen. And also you need to have a good collaboration with your turbine vendors for appropriate technologies. It is a less mature option than electrification, but it's got it looks quite attractive because there's a lot less modification of an existing plant than retrofitting electric drivers. Carbon capture and sequestration at the bottom of exhaust gases, quite familiar, I think, to most of the audience. And it has been considered extensively for LNG sites. So the challenges that we see are that the plot space requirements required to capture the flue gas and cool down are quite significant. It is a potential option for brand new build facilities who are considering carbon capture and underground sequestration at the very early development stage. There's also the offset or compensation of emissions through the use of carbon credits through biosequestration of carbon in vegetation, so forests and bush grasslands. It's a pathway. There are national and international schemes which provide verification and assurance that the sequestration of that is credible. There's a quite new area that's opened up in the commercialisation of gas sourced, which is not from fossil era, but actually man-made or human-enabled, sorry. And there's two sources of that. There's bio-LNG and separately synthetic LNG. So bio-LNG is basically methane, which is produced by anaerobic digestion of organic matter, so livestock product manure, agricultural waste, food waste. So the biogas ends up primarily a mix of CO2 and methane. So you take that and you can upgrade it by removing the CO2 and some of the other non-methane contaminants. Then you can take the methane, process it and cool it to LNG under conventional equipment. So bio-LNG, like synthetic LNG, can be blended into other gas fuels, and that reduces the overall carbon intensity of that fuel. Biogas is quite advanced in the EU now due to legislation. The legislation has been brought through from the early 2020s to both encourage emission reduction, but also to reduce reliance on imported Russian gas. So I'll just go to the next one for synthetic LNG or liquefied synthetic gas. So this I find really interesting. The concept of synthetic LNG is methane produced by using green hydrogen as a feedstock, reacting it with carbon dioxide to form methane and water. So the methane then is cooled and liquefied in the conventional LNG process and shipped in conventional and existing LNG value chain infrastructure. So as part of the circularity, CO2 would come from direct air capture or industrial generation. So for example, either the biomethane off gas we talked about or CO2 capture from flue gases. I think the concept of generating green hydrogen and then conversion to methane is basically based on the practicality of using the existing LNG infrastructure, which we have. So I know the last time I spoke, people were very interested in hydrogen and where is hydrogen in the energy mix for the future. Large-scale hydrogen is still pretty challenging. So liquid hydrogen, as the scientists know, only occurs at minus 253 degrees Celsius, a lot colder than LNG at minus 161. The power requirement to liquefy is basically 8 times that of LNG. The requirement for cold temperature materials to make that happen is highly challenging. Liquid hydrogen also, it has the advantage that it's got a lot more heating value, so 2.5 times more heating value per unit mass. However, it's a lot less dense. It's about 1/6 the density of LNG, so you would need to store more of it to get the equivalent heating value. So storage and transport costs are again more. So this is where the attraction of actually using hydrogen to turn into methane to use existing infrastructure lies. So this chart shows the biomethane production. Biomethane is more mature, obviously, than liquefied synthetic gas, but you can see it's predicted to have a steep compound annual growth rate of 13% year on year, and that's driven strongly by transport demand. So EU legislation, for example, is predicted to mandate an increasing percentage of bio-based fuel through to 2050. The International Maritime Organization, the IMO, they've just released their 2028 greenhouse gas emissions regulations, and they will require ships to adopt increasing biofuels in their usage or pay significant penalties. So now, as a part of greenhouse gas mitigation, we've been talking a lot about CO2, but methane is another one that's become quite front of mind recently. So the focus in the recent past on CO2 has been the main culprit of global warming. However, we know that the global warming potential of methane is 25 to 28 times higher than CO2. So the emission of methane through the production of LNG and gas, if uncontrolled, can actually more than offset the positive impact of LNG versus coal. So because of this, the industry has taken a very serious and stringent approach to methane intensity in LNG production. There's the Oil and Gas Methane Partnership, known as OGMP. It's a voluntary initiative that's led by the United Nations Environment Programme, and it provides a framework for oil and gas companies to improve their accuracy and transparency in methane emission measurement and reporting. So the signatories to the OGMP can be certified through different levels of verification, from source level engineering type calculations through to emission modelling, and then finally through to quite advanced drone imaging of production facilities. So the most recent industry average of methane emissions is less than 0.15% of methane, and there are a number of sites which are even well below that number. Am I going for time? Oh, pretty good. So yeah, so the common industry goal to reducing methane emissions to near zero is driven by all parts of the chain, the suppliers, the customers, and it's underpinned by country legislation and policy. So along with the elimination of venting and flaring, which the industry has been working on for a long, long time, it does reflect the growing recognition that climate change is multidimensional in cause, and there are many approaches to mitigate. So pathways towards net zero have got to be dynamic. I think what's important to remember is that the current energy system we live in has taken close to 200 years to establish, and it's going to take time to change that, but it is changing. So the world still has the net zero ambition by 2050. It's still a commitment by the vast majority of the world's countries and organisations that can enact change. Even though the politics is changing, the world still believes that we have to do something significant before we reach that moment of 1.5 degrees. So we have to be thoughtful that we don't allow that saying, perfection to be the enemy of good. There's not one silver bullet solution. We have to be open to different solutions that have flexibility Organic growth is important, and we do need a broad mix of energy options still to be able to support the world's development and growth into 2050 and beyond. So that actually concludes my presentation. I thought I'd be well over time, but seems to have turned out quite well. Hopefully I've managed to share something with you which is of value. I've spoken for a lot now, so I'm happy to have a discussion. Maybe you guys ask me some questions and also online.
Great, thank you very much, Carolyn, for a wonderful presentation. And I should also state that Carolyn is a technical advisor, so maybe can't talk about policy that too much. He's fine. Any other questions? So any from the room? Yes.
My name is. Thank you. My name is Arif Susatyo. I would like to ask regarding the fuel source of the LNG vessel. So as we know, usually vessels utilize marine fuel oil with the low speed diesel engine, and the LNG has boil off gas. So my question is, for LNG vessel like from Australia to Japan, intercontinental like that, is the boil off gas utilized for the MFO engine, for the marine fuel oil engine, or is it full LNG? And the second question is, how is the fuel compatibility of the natural gas to the low speed diesel engine? Thank you.
All right. So yes, so absolutely. Most LNG vessels these days will utilize boil-off gas for the main journey. I believe that when you're in port, there's different requirements depending on the port, and it may be a requirement that you might have to use a certain type of fuel when you're actually in your port of where you're moored, where you're discharging, or you're at a port where you're doing some other business like repairs. So yeah, so absolutely, that's been one of the I guess selling points of LNG carriers. Even before we talked about, we started getting into emissions reduction, is that the use of boil-off gases has been far more environmentally positive than the use of marine fuel oil.
So still utilize marine fuel oil.
As I said, I think it all depends on what the requirements of the ports are. Yeah.
But for international waters,
international waters, they would be mostly using boil-off gas for sure. Yes.
Oh,
Yeah.
okay.
Yeah.
Thank you very much.
Yeah. It's cheaper. It's big. You have as I said, you've got a source of boil-off of 0.07% per day. So you have to do something with that gas. You either recompress it at cost, or you use it as your source of motive power. Yeah.
Yeah.
Hi, thanks for the presentation. I'm wondering, you mentioned that there's going to be a supply shortfall in LNG in about that 2034 year.
Mm-hmm.
But at the same time, the IPCC, the IEA, they say that all of the existing, the existing and planned infrastructure is already going to exceed the 1.5 degree budget, probably the 2 degree budget as well. So how does a company like Shell, yes, we may have a shortfall, but shouldn't we not be selling this gas when there's already too much for, say, future?
So I'll try and answer from the technical perspective. So the shortfall comes from the projected demand and the projected supply. So like when it's a case of the expectation is there's going to be a demand for 700 million tonnes, and at that time there's actually not enough capacity to produce that 700 million tonnes. The 1.5 degrees, I guess, it's a more emotive question, and I don't think I can do justice to it like in this forum. Yeah.
Thank you. I'm Adrian Williams. Just a couple of interrelated questions. I had always thought that LNG was compressed to shipping. Is that right, or is it just shipped at ambient pressure and cold? Then at the degasification end, I'm just interested in the processes that, or the options that might exist to recapture some of the energy value in that cold gas.
Absolutely. So you're right. So it is shipped at ambient pressure, or just basically 50 millibar gauge above ambient pressure. So that's where it comes to the minus 162 degrees Celsius. And on the regasification side, yes, the cold is actually used. So in Japan, one of the uses of the cold is actually to freeze fish for sushi. And actually, having visited some of our buyers in Japan, they very proudly served me sushi, which came from, had been frozen by LNG regasification. There is also some other options to convert the cold into sources of power. That's a really good question. Let me get you some details on that. Just off the top of my head, I don't have it there.
One more online.
Yeah.
I'm going to choose it. I have the power to choose a question from online, and I'm going to choose this one because I actually have an interest in it myself. So thanks, Peter, for your question. So it's both do carbon capture and storage as research areas.
Yeah.
So in your presentation, you talked about carbon capture and storage, but you sort of somewhat downplayed its importance. So why is that? So do you think, and she also spoke about other technologies such as biomethane and synthetic gas. Is it a cost issue that you're looking at, or a technology readiness level that you're talking about, or what's the reason for that?
So within the frame of using carbon capture and sequestration for flue gases from an LNG facility, what we found is that there's obviously an enormous amount of flue gas that comes from the gas turbines, and the size of the plot space required to gather that and to cool it down. So you have to cool it from 500, 600 degrees down to, I think, 75 degrees. Actually, for most of our existing LNG sites, we don't have that plot space actually available. So it's in terms of retrofitting, it's probably not an area that we're looking closely to, but if we were to build another brand new site, it would be something that you would bring into consideration at the very earliest stages. Yeah.
And have you done it? Is there a cost comparison for biomethane and synthetic gas versus the standard gas level?
Synthetic LNG at this point in time with the green hydrogen is very expensive. So green hydrogen, by producing green hydrogen, that's quite an expensive undertaking. Biomethane, we actually, Shell has a few small, you could almost say pilot processes in Europe. So, and they're in the hundreds and thousands of tons as opposed to millions of tons. So there's a bio-LNG bus fueling station, I think, in the Netherlands. So we're starting to, the fact that we've got the pilot plants going up kind of suggests that that is a more positive kind of chance of success as we go further with the technology. Yeah.
Thank you. With respect to contract structures, what would be a typical range for the percentage of Australian gas, for example, that is put aside for spot pricing as opposed to long-term contracts?
So that's kind of getting into policy and contracts, and I don't have the knowledge on that, I'm afraid. I'm sorry. Yeah. So we do, so Shell Australia does supply to both the domestic market and the export market, but the details I'm not privy to.
For the process you showed about the creation of synthetic LNG,
Yep.
I was fascinated you had reliant surplus electricity from renewable power. And I'm thinking that the reason it's surplus is just as a way of kind of lowering the cost of that. I mean, it doesn't have surplus, so it could be, there's no reason why it has to be surplus electricity. It would just be that would be a way of lowering the cost of using it. Would that be correct?
I think probably when we look at synthetic LNG, there's the projects that we look at are in the Middle East. So there's quite significant amounts of renewables available there. So I think, yeah, in the phrase of surplus, it reflects a location where you have ample supply of renewable energy. Yes, yeah.
And we'll take another one from online. So there's been a lot of interest in geological hydrogen. Do you see that as having a future or a bit of a niche?
Geological hydrogen. So I don't think too much about that, to be honest. Yeah. I mean, like, you know, we go through the rainbows of the different hydrogens.
So I think you've answered the question.
Yeah.
Thank you for your presentation. I found that very interesting. In being a technical expert and looking at all those different directions and new processes for lowering emissions that are coming into place, how much do you need to consider what markets those might be sold into, the project costs and things like that? Because I imagine that Australia's not using a lot of that LNG. We've got other alternatives, you know, may not be cost effective for us. So how finely balanced are those things? And how much does that affect, you know, what you look at from a technical perspective?
Yeah, absolutely. I think that's probably the benefit of a global company like Shell, like where we operate in most countries of the world, and yeah, every country has its own perspective on legislation and where they see themselves in terms of emissions and net zero. But also it's actually influenced a lot by our customers. So particularly our Asian customers, Japan, Korea, Taiwan, it feels like there's a very strong sense of doing the right thing, kind of like, you know, there's a lot of integrity. People would like their LNG to be green LNG. There's a request for certification to make sure that our methane emissions in the production are low. There's a request for certifications that you know, we have offsets. So every country, every project, every supplier and every customer actually has their own little bent towards it. But I think overwhelmingly what we see is that the world is definitely looking at we need to have net zero by 2050. So it's not just it's not just lip service, I think is what I'm trying to say. We do see a lot of people wanting to put their money where their mouth is.
So is there more attention directed at some of those technologies, those new technologies than others?
Yes, there will be. Yeah. And Australia is quite like a different has a different kind of focus and culture towards emissions than other countries. So particularly in Europe, you know, there's a lot more stringent legislation, the Renewable Energy Directives 2 and 3, which basically really they encourage, but they also, in a sense, force companies into looking closely at what they're doing over the next few years. Yep.
Hi, Carolyn. Thanks very much. I wanted to ask you about, you mentioned a couple of times, I think, that the emissions from LNG is about 50% of what is sort of coal.
Roughly, yeah.
Roughly.
Mm-hmm.
So now, I'm sure that I've read a couple of articles in the last couple of years, probably in the conversation that around sort of leakage and fugitive emissions, including with shipping.
Yeah.
That then take emissions much closer to coal. And so I'm just wondering, can you comment on sort of emissions with shipping and whether specifically that 50% is likely to include those studies, or is it a figure that you've taken sort of potentially before, you know, prior to those studies?
So the methane, let me go back, maybe I have a slide, whoops, on methane, whoops. Sorry. Yeah, so the 50%, I don't think takes into account the any emissions, but on the methane emissions, the fugitive emissions, I think the number is if in the production process you have more than 0.2% emissions, thanks Franca, then basically the use of LNG is kind of on a par with coal. So yeah, this is the slide that talks about the OGMP and the methane emissions. We've got that 0.2%. And as you can see, from 2017 through to 2023, which was the last kind of like, I think, full cycle of OGMP, the actual emissions measured and verified on an industry average have halved, and bringing it below that 0.2%, which then puts us in the space that if this is correct, if the 0.15% is correct, then LNG is still much better than coal.
Is that more accurate than it was, say, 5 or 6 years ago?
The measurement now is definitely far more accurate, yes, because of the measurement and the verification through the oil and gas methane partnership. Yeah.
Is that because the leakage at facilities is better captured?
Yes, yeah, absolutely. Because I mean, you can, if you measure something, then you can see it, then you can actually do something about it. Yeah. Does that answer your question? Yeah.
Where there was a study that was showing that there's a lot more leakage during shipping than previously understood.
Yeah, I'm not a marine person, but let me go back to this slide. So on the right-hand side, there's a engine technology, and it talks about methane slip in engines. And so you can see that the newer vessels on order predominantly have a focus on engine technology that is lower methane slip. Yes.
So is that the engine's usage rather than the leakage?
Oh, okay, then all right. I think that's the technology of the engine. So the leakage, if you're talking about an LNG carrier that is actually leaking.
That's how
okay, then all right. I've not really heard of that. I mean, for reasons even beyond emissions, you don't want methane to be leaking anywhere, right? It's an explosive hazard. Yes, yeah. So I would expect that the integrity of the vessels against leakage would be fairly high, as in like there'd be very low leakage.
I've had a follow-up that geological hydrogen is silver hydrogen.
Oh, okay then. All right, thank you. I'm gonna Google that. Yes, I know the green, the blue, the brown, the grey, the black, but silver. Okay.
Another question about the demand forecasting there.
Yeah.
Does that include in hydrogen and ammonia and things like that? So you're having that's what demand forecasting for LNG does include the impacts of other energy carriers.
Oops. There's actually, this is not about a shameless plug for Shell or anything like that, but if you go to the Shell website, they publish something called the Shell LNG Outlook, and these slides come from there, and it's actually quite a significant level of research into the energy kind of like future that the world sees. So from the strategy perspective and also from the demand. So given that this slide here shows me that there's some data for LNG engines, methanol engines, hydrogen, ammonia, other, I would say that the demand is quite specific and quite granular. Yeah.
I think I've got a heap of other questions here, but I think we've put you over the pump for a fair while now. So thanks again for your wonderful presentation, and thank you for a very insightful question from the audience, both in person and online. And once again,
thank you.